Okay, so after our discussion on the parity spin and isospin of the ground state of deuteron, let us now do a quantum mechanical analysis. Basic, again not very advanced, this will be a basic quantum mechanical analysis of the ground state of deuteron. Fine. Now before we do that, let us consider the following assumptions. Assumption number 1. Following assumptions. The first assumption is that number 1, the deuteron 8 consists of two particles of roughly equal mass. What is the mass? M. So this means that the reduced mass of system is half m, right? The second assumption is that the force between the particles is short range and attractive. So number 1 short range, number 2 attractive, and number 3 is acts along the line joining the two particles, that is, it's a central force. Now in fact this assumption that it is a central force, this is not correct, because if we assume this, we cannot entirely explain the quadrupole moment. Okay, and so we have to consider non-central forces as well. But right now, for our basic quantum mechanical analysis, let us assume and see what happens. Okay, the third assumption is that the force can be derived from a potential. Now when I am saying this, I am excluding the velocity dependent forces. So no velocity dependent forces, they become actually important for high energies, and we are considering low energy. Come on, we are considering ground state. Fine. So let us proceed. Okay, fine. Now you see the force is attractive everywhere, and so this means that the potential is negative and it decreases with decreasing distance. And again we have considered that the force is short range, so this means that the potential vanishes for some range of the potential. Let us consider the range of potential b, small b. Let us consider that small b is of the order of say 3 Fermi meter or so. Now we will consider a square wave potential, right? So let me write down. So basically V is equal to minus V0 for R less than B, and then this is equal to 0 for R greater than B. So what is V0 basically? V0 is the depth of the potential. potential, and as I have told you previously, B is the range of the potential. Fine. Now we have already discussed about the fact that our L can be either 0 or 2. However, now let us consider the fact that L is 0 only, although we will see that we need some admixture of L equal to 2 later on, but for the time being, for the sake of simplicity, let us consider L equal to 0. Now, for this L equal to 0 case, the nucleons, what? They are basically then in the S state, in the ground state. So this means spherically symmetric. Okay, so let me write down the wave function. So let me write down the wave function. Psi r equal to ur by r. Okay, where this ur satisfies the equation, let me write it down, d2u dr2 I am just considering a basic square wave potential. This you have done in your graduation days. Yet another example of it. Okay. So this is UR satisfies this. Now if I consider the square wave potential, this one, yeah. Okay. So then if the equation satisfies this square wave, so we will get d2u dr2 plus is equal to 0 for r less than b, and d2u dr2 minus alpha square u equal to 0 for r greater than b. Fine. Where basically we have this alpha square is equal to mb by h cross square, and kappa square is equal to m by h cross square v0 minus b. The total energy of the system is of course negative of the binding energy of the deuteron. What is the binding energy? Let me again write it down. So the binding energy here is 2.225 MeV. I am excluding the error in the measurement. So now let us try to solve this equation. See, I am considering the S state only, L equal to 0. So you will not find any centrifugal terms in the potential. In many books you will see that they have again solved the Deuteron ground state problem considering a generalized case, not just L equal to 0. There you will find L dependent terms. Say for example S.N. Ghoshal's nuclear physics book. If you see the same ground state derivation, you will find that it is little bit more complicated since it is a more generalized scenario. ठीक है? So this is what I have done, right? So this is the relationship between depth and range, and after that we are trying to find the normalization constants which we can get from this integral of 5 square when done over all space. if the integration of this phi square over all space, if we do that, we will get this one normalization, and so this is the condition, and from there we can get a1 and a2. And so if we put these solutions over here, then after some simplification you will get this relationship. Fine. So after this we can get the constants a1 and a2. We can get a1 and a2. Okay. Any questions till now? See, in this analysis of the ground state of Deuteron, we have considered three basic assumptions. Next, we have considered the simplest possibility, square well potential, simplicity. Next, again, we have not considered any L dependent terms in our analysis, that is, any centrifugal term we will not consider, anti-centrifugal effects. So we have got rid of all that. We are considering only the S state. So these are the simplifications of these calculations. So what we have done till now, the Deuteron problem, we have discussed the assumptions, then simplifications. This is important. Okay, don't forget that we have got two simplifications. One is the choice of this simple square well potential, another is considering this L equal to 0 part. Two simplifications, then we solve them in a quantum mechanically, and we obtain the relationship between depth and range. This is important. So you can expect questions like solve the Deuteron problem for the ground state and obtain relation between depth and range. And next, finally, how do you get the coefficients? So we will get the coefficients using the relations that we have discussed from this relation and also this relation, these two relations. Okay, so basically let me write down. We can get the coefficients mainly from this relation A over here and this relation B. So from these two relations we will get these coefficients A1 and A2, and already we have got this relation between depth and range. So this completes our very simple picture. Okay, now we will go, as I was telling you, into little bit more details. Now previously, remember, we obtained this relation K cot kappa B cot kappa B, this is equal to minus alpha. Now we can rewrite this as x cot x is equal to minus alpha B, where this x is equal to kappa into B. Now you see, we already know. What do we know? Is that B is of the order of 3 Fermi meter. And so, what? Also we know that capital B is equal to 2.225 MeV. Okay? So, the value of alpha square mb by h cross square, right? So if we use these values of B as well, then from here we will get alpha is equal to 0.232 Fermi meter inverse, and this gives us alpha into B less than equal to approximately 0.7. Now what we are going to do is we are going to draw curves. Let's go to the next page. So let us now draw curves. Y is equal to cot x and y is equal to minus alpha b by x, and the intersections will give solutions for the relation that we previously obtained, that is x cot x is equal to minus alpha b, right? So let me start doing that. So as I was telling you, so I have drawn the two curves over here, right? Yes, y cot x and minus b by alpha b by x. Remember, alpha b value was 0.7 or so. So I have put it the value, and here the intersection will give us the roots. So what do you see from here? You can see that the roots are approximately equal to, but slightly larger than this. You see here. So the roots, one, another one. So basically what I am observing is that roots are, you see, slightly larger. Larger than your n plus half pi. See these values when n runs from 0 onwards. Now the correct solution to take will be what? This one, the correct solution. So let me write it. The correct solution will be this, approximately half pi. And why is it that? Because if this chi into b is greater than pi, then the wave function, so if is greater than pi, then you see the wave function would have a node at equal to pi, and this would not be the, and this would not be the wave function of ground state. So this means that here we can rule this one out, right? So this is my solution. Fine. Okay. We therefore have a very important result. Now look into the behavior of the solution. So how does it look like? Basically what we have is this. Regarding the behavior of the solution, we have the value is less than pi and approximately close to, whereas greater than pi by 2. So this is our ground state scenario. Fine. Now let us try to find a better approximation. How do we do that? Let's see. To find a better approximation than pi by 2 less than approximately v less than pi. Let us try to do that. Now to do this, let us put b is equal to pi by 2 plus epsilon, and then we will substitute this in our, and then substitute in this equation. Remember this one, the original relation minus alpha. Fine. Now if we do that, then we will get as a result epsilon cot pi by 2 plus epsilon, this is equal to minus alpha v. Now let me go to the next page. Okay, now what I am going to do, see here. So basically this alpha is somewhere over here. Now let me put alpha very small and see what happens. So this is what I am going to do. So if alpha is small, then your cot pi by 2 plus epsilon, this is approximately minus alpha, and this means that epsilon will be equal to 2 b by pi. And thus from the previous relation, that means this relation, we will have overall, remember this is what we are putting over here. So this is important. These two are our defining relations. This one and this one, they are changing, showing us the change. So we will have basically, so we have pi by 2 plus twice alpha b divided by pi. Now we already know as is greater than equal to 0.6 Fermi-meter. Remember. And what was the value of epsilon? Can anybody tell me? एक बार देखे ना जाए. So this is the value. So this we have obtained previously. Now if we use both of them, then we can have basically this scenario. That means, what does this mean? This means that basically that the depth of potential is very much greater than binding energy. Okay, so this we are getting from this relation, these results we are getting from this relation itself. Okay, now this we have just obtained. Now you see, if we observe this, it follows that there cannot be any excited state. How? Can't have any excited S state. How? Can you tell me? You see, let me use a different color. Okay. Let's see. Let's write then. Since you see the ground state binding energy is very much greater than what do you say? Ground state binding energy is greater or lesser? Tell me. I have just now showed that the depth of potential is very much large. So, ground state binding energy, it will not be greater, it will be lesser, right? Don't sleep over, students. Very much lesser than depth of potential. So, from this previous relation, that means this relation we can write down this pi by 2 0 into V pi. Here what we have done, we have basically have done this. See, this is K, not kappa, K0, and this K0 we are getting from this form. However, if the binding energy of first excited, not S, first excited S state is given by beta square, then we must have root over K0 square minus beta square, this thing, greater than 3 by 2 pi. Why have I written like this? This was the ground state, then this has to be got to be the first excited state, right? Now I am wondering whether the first excited state will be an S state or not. This is what I am trying to find. Whatever be the case, the first excited state will be close to 3 pi by 2, okay? And this is what I have written over here, see? 3 pi by 2. So we must have this scenario. However, this very fact contradicts. This very fact contradicts this relation. You see? And so, what does this mean? Tell me. This means that we cannot have an excited S state. So, we can't have excited S state for Deuteron. Any questions? Anyone? So we have basically discussed about the ground state of Deuteron, the relation between depth and range, right? This we have obtained here, you see. relation between depth and range, the normalization constants, how do we get. Next, we found the numerical solution in a graph format. We have tried to find the solution, and we have seen this is the ground state or so, right? And after that, what did we do? After that, we tried to investigate that if we can have an excited state for Deuteron. So we can't have that a state for Deuteron. Next, what we are going to investigate is the following. We will now try to show you that we cannot have. So this is number 3 investigation. Okay. Number 2 was this. Number 2 is here. We cannot have an excited state. This is what we are discussing. And number 1 was your Deuteron problem. So I will be basically talking about 3 important this will be number 1. I will be talking about 3 important quantum mechanical descriptions and derivations for Deuteron. So number 3 is the following. We will show you that there can't be any bound states with higher angular momentum. Okay. Now, to see this, let us start. First, we will write down the radial equation for any angular momentum. This is what we are going to write, and so 2u dr square plus m by h cross square e minus v. Now you will see what we have done was very much simpler. There will be a minus term, and this is where this L dependent term, centrifugal term, comes into play. Okay, now this is the generalization of which equation? Can you tell me? Can anybody tell me? Remember, previously we talked about this relationship. Yes, right. This is the one. Right now, the relation that we are writing is a generalization of this relation, where there is no L present. Okay. Right. Okay. Now, so if we compare this with the first term, then we see that this is equivalent to an S wave radial equation with modified potential. And what is the potential? You see this. So the potential is, let me write like this, V effective R, this is equal to VR plus H cross square L into L plus 1 divided by M R square. Okay. Now you see there are 2 terms. First term, this was already present. This is the new term. Okay. Now this is the potential of the centrifugal force. what do you think its sign is? You see, the positive sign. Its sign is positive. Okay, so this means, let me write it down. Positive sign, this means repulsive. Okay, and also what can you see is that is the following, very important. This increases with increasing L. Two features, this is repulsive and this term increases with increasing L. Two very important features. So since this increases with increasing L, so this means that the binding energy of the lowest bound state for a given L decreases as let me write it down. Yes. Since the centrifugal term, you see, increases with increasing L, so this means that the binding energy of lowest bound state for a given L, this decreases as your L increases. Fine. So now we are going to show that there is no bound P state, lowest L not equal to 0 state. Fine. So let me write down, let me continue from where I was doing. Okay, so we will consider lowest L case, that is lowest L not equal to 0 case, which is L equal to 1, since the others will be more repulsive, right? So there is no point in doing the investigation further. So with this, let us write down our solutions. Which solutions? But not solutions, but this particular equation. Let me rewrite. For L is equal to 1, rewriting radial equation for L is equal to 1, we have dr squared plus minus 2 by r square into u is equal to 0. This is for r less than b, and the next term is du dr square minus alpha square minus 2 by r square into u equal to 0 for r greater than b. Now you see, only these two terms are extra over here compared to the previous case. Note that now your this kappa and alpha, they correspond to the binding energy of lowest P state. Fine. Now the least well depth. This is what we will investigate. The least well depth is required when this state is only just bound. That is, what does this mean? This means that when alpha is equal to 0 and kappa is equal to k0. K0. So, yes. So, if we put k0 into r is equal to x, then our equations become dx square plus u minus 2u by x square to 0. This for x less than k0b, and next d2u dx square minus 2u by x square equal to 0. This for x greater than k0 into b. Now the solution of second equation, this one, with boundary conditions will be u is equal to a2 by, this is 2, a2, just a second, a2 divided by x for x greater than k0 into b. Now the first one is quite tricky, the solution. Let us do some mathematics to find its solution. For that, we have to first rewrite this equation. See, now I am using v, not x. U instead of u, now I am writing v. What is v? Just a second, I will write it down. So now here your v is just x into u, and after differentiation we will get this is done so that we get a solution which is easy to work with. Again, for x less than k0 into b. Now you will get this after some rearrangement. Now, since u is equal to v by x must vanish for x is equal to 0, so the correct solution will be 1 by x dv dx is equal to a1 into sine x. Again, x is less than k0 into b. After integrating, this will give us we will get V is equal to X into U is equal to A1 sin X minus X cos X. See, every time I am writing the solution, I am putting the condition as well. This is important. Now, matching of the solutions. Matching of basically function xu on boundary x is equal to k0 into b will give us the continuity equation, which is here x is equal to k0b. So from here we will get k0 into b sin k0 into b equal to 0, and the smallest positive root of this equation is basically k0 into b equal to pi. What does this mean? See, what I am saying is the following: k0b into sin k0b equal to 0. From here, the smallest positive root of this equation is k0b equal to pi. Fine. So this means that a bound state for L not equal to 0 case, this is the second case that we are doing, can exist only if k0b is sort of greater than pi. This is the smallest one. Remember, the higher ones will have even more greater values, right? So this is what I am written. However, this very fact contradicts our previous study here. The one that we discussed here. See, this we found. So this contradicts the fact that k0b must be between pi by 2 and pi. So from these two observations we find that the deuteron can't have excited state. Now you see, if the depth of the potential would have been more, say 5 times more, 10 times more, with the same value of the range of potential B, then probably we can have excited states for deuteron. But with the current V0 and B, we cannot have any excited states. Any questions, student?